this presentation is, I have included slides which I would not have if I was giving a formal presentation. I've just taken this opportunity of like a 1 hour slot and kind of prepare presentation from a very intuitive point of view. You'll be able to understand because I'm familiar that most of you are not doing 3D. So just also some introductory slides to help the case so that you can follow through, okay? Now it's working. So I'm going to take this opportunity to define first what is non-rigid structure for motion, okay? Slowly introducing the concept, and this term organic prior has not been used in previous literature. So I'm going to take this opportunity to define this term for the first time. Okay, so let's see this video and why this is important. It's going to get
used on dozens of features like Transformers, Age of Extinction, Pacific Rim, Teenage Mutant Ninja Turtles, and most recently, something called Star Wars: The Force Awakens. Well, I'm a big fan of that. Jerome Mallet and Christoph Bregler, for their design and engineering of the ILM Geometry Tracker, the Academy presents a Technical Achievement Award.
So this guy, Christoph Bregler, first started doing this promotion in the year 2000. And for his profound work in non-rigid structure for motion and motion capture system, he was also awarded, you can see in 2016, this Academy Award for having blockbuster movie, Hollywood movie. So what's at stake with this branch of research, basically. And he is important because our work is also trying to find new patterns on what he devised with matrix factorization in the year 2000. Okay. And he was very successful even commercially and academically. So he was a Stanford graduate. Let's understand structure for motion. Those who are not, you can think in terms of black box. You are given multiple images, you throw into like a neural network, if you can think in that term, and what comes out is a structure. Okay. So that's like from an intuitive viewpoint, you can understand this field, But mostly when people say a structure for motion, it goes synonymous with rigid structure for motion, where the structure is not moving. So when I talk about non-rigid structure for motion, what you have to understand is that the subject in the scene is also moving, and you have to precisely reason about the structure and the camera purview. So that's basically non-rigid structure for motion in a very intuitive sense, okay? Then the question comes like, okay, I have already given the Oscar Academy Award winning clip, so you know what is at stake, but let me define formally. And it clearly says in the first paragraph of the textbook is that non-rigid state appears at all scale in nature, from human body, its organ and tissue, to tiny bacteria and microscope protein molecules, and it goes on and on. And then what is important for your new researcher is that to understand that it's very important even for pattern recognition and computer vision application. Okay. Let me take this opportunity to also define a bit precisely what I mean by non-rigid in mathematical terms. When you deform this shape, the local distance changes here. So when it's rigid, the distance, the transformation, the distance is preserved. When you deform the shape, the distance is not preserved, changes. Okay. So that's also a formal way of understanding or constraining this form. Sometimes, science is driven by money. So if you are not something that didn't interest you from theoretical curiosity, but there's also monetarily motivation why you should study this field, at least in coming future. There are some survey, I've taken this from this source. In 2019, they also made the survey that AR and VR is really gonna take the market in the coming decade or so in terms of technology. So there is also a monetarily motivation why this field is so important. Okay, and let's see some practical application. People love movies, So you can see how they are able to align the model correctly if you know correct motion and correct structure. People say AR, VR, but I want to devise term called enhanced reality. This is in between the two, let's say. And this is very successful in entertainment industry. Not only that, uh, if you're looking for medical application, bypass surgery, all these things, they need 3D model of deforming objects for automating the surgery for robotics. So then it provides a feedback to the robotic system for precise surgery. Okay. Here, it's on your phone also, motion capture system. It was a startup from Swiss, Zurich, I would say. It was adopted by Apple later, and an emoji is in your iPhone that works on motion capture system and non-rigid structure. Okay, so a lot of motivation, but when you go to literature to do the survey of this field and you got interest in this field, there are hundreds, if not thousands of papers on this topic. And when I started this topic, researching this topic 6 years back, I was clueless, basically. So why I did this work, the reason is I was looking for a unifying principle. And if I can improve that, I can basically improve all the derivative work. And that's where Christopher Bregler, the guy that you show in Academy Award, becomes important for me, because he's the first who devised this. So when you track back, the root lies here with this work, basically. And it was also kind of derived by Tomasi and Kanade work. He did it in 30 years back, basically. So there's an exhaustive list of literature here. But then when you track back and try to filter, which is a very painful process, what you'll find, there are a few works which challenge their method and kind of tries to improve it. And those are, I have highlighted in red. Okay, so this was first of motivation why I started doing work on this. It's such a commercially driven problem, and there are very few people who work, and nobody's trying to kind of condense and come to a unifying principle of changing or improving the foundation of the work. So now let's define the term here. As I have already intuitively recover the 3D structure of a deformable object from multiple images. So that's the definition. And it's also defined like this in the seminal paper. Your input is feature key points, tracked along multiple frames. And the goal is to estimate camera and 3D structure per frame. You can intuitively think like this. So you're given track points, right? And if you track it, it looks like a trajectory. Imagine it, right? If you plot it in the MATLAB or any framework, it looks like a trajectory. So those who are from signal processing can also think in terms of signal processing about this problem. And the goal is to basically recover 3D from this 2D trajectory over multiple frames. So that's like from an intuitive viewpoint. Okay, so it looks like a simple problem. What's the challenge? Where the challenge is coming from? So let's understand this a bit. I'll not say all, but let's understand a bit. If the subject is not moving and I can take its projection over multiple cameras, I can basically constrain the motion of each point. Because it's not moving, I can constrain it over frames using multiple view geometry and epipolar geometry. There are tons of work there. Okay, it's not moving, so I can basically constrain every point in 3D space using correspondence of 2D. However, let's see the non-rigid part. I don't know how actor is going to behave in the next frame. So it's basically unbounded to do whatever they want. I cannot constrain the motion of the object. Okay. And that becomes like, okay, in that case, if you cannot constrain, what you can do is basically solve single image 3D, but you know that it's a ill-posed problem. It's very hard to solve. And that's where one of the challenge comes from. Another important challenge that comes is because camera can capture only relative motion, because if the camera is also moving, we cannot disentangle camera motion from object motion. Okay, disentangling will become very tough. So these are the two challenges. So what looks like a simple problem to you turns out to be a very challenging and painful problem. And what happens when you have something which you cannot constrain? In any computer vision problem is you make some assumptions and prior so that you can solve the problem, at least from an application viewpoint, if not from a mathematical viewpoint. Okay, I went back to the literature. And why I'm motivating so much is because we have went back to 30 years here with this work and kind of tried to revive it. So if you track back the literature, there are tons of priors, physical prior, smooth surface, this, that, there are so many. I just listed some of them in this couple of days. Then you go to statistical prior, there are many more. There are other priors, but I have not listed them. So when I was doing this work, I realized let's keep the assumption and prior same as the seminal work. So I kept this Lorange, because this was also proposed in the first work done in this area. And my practice of this work is that it kinds of hold for most deformation, low rank shape. You will understand what I'm basically mean. Low rank shape has to do with matrix, okay? Because this work is about matrix factorization. Another assumption is orthographic camera. Okay? So orthographic camera, you understand if you have taken a course, it kind of preserves the alignment and scale of the scene space. If we take perspective camerization, the problem becomes more difficult to solve. So, and this was also used in the seminal work, so I kept the assumption same. Okay. Everything fine. There are so many methods to solve, and I have already said that why I used classic factorization approach, at least from unifying principal point. But let's understand also why I went there from other. There are other motivation I went to matrix factorization. And one of the key was this. What you see here is a table, and there was a challenge conducted in year 2017 at CVPR 2017, basically. And this is the method which won the challenge, okay? And kind of I got a bragging right for that I won that challenge. Here is my supervisor, Home Dong and Yu Chao. But although we won the challenge, but it left us with lots of questions. And the question was this. This was the method on which I developed my work. Okay, so my work was a development not from a theoretical point of view, but from a constraint point of view. And this was the method which was CVPR 2012 best paper. And it was developed by my supervisor. They won the best paper at 2012 CVPR. What hit me is this stats, because this was evaluated by third party. We didn't evaluate. That this SPFM work that you are seeing is developed on this method, like it was superior, at least in terms of theory. But when I put into practice, it performed substantially lower than that. So PTA was developed before this. So why they won the best paper award is because of the theoretical contribution. SPFM, this simple prior free, they call it, method, was noteworthy, but they were not able to perform well. So what I realized, there might be something we are missing with the theory. So that also gave me additional motivation why we should go back and both of these are matrix factorization approaches. Okay. So that was the motivation, that there is a theory and practice gap, which we want to mitigate, let's say, with this. Another motivation is coming from practical application. Let's see this structure for motion. It's a rigid case. So if you have visited New York, you know, this is the famous Statue of Liberty, right? And what we can achieve is not only 3D, good 3D, but I can render this scene at several scale and kind of give, and this was also adopted in phototourism from Microsoft, developed in around 2010, 2012, okay? Very hugely success in terms of application. But if I go for rendering non-rigid scene with reconstruction, there are no algorithms basically. And what I mean by that is this. So that's what a point I want to make is that it has a solid theory with provable guarantees and it works. So there is theory, there is practice, everything works fine. Not only from 3D viewpoint, if I want to do rendering, I can also do that. Okay, so what you saw is here is a rendering of 3D. But if I have to do rendering for non-rigid, see this. So they employed like thousands of engineers to do this clip. Let's see. So they were developing this mesh processing because they didn't have the 3D, and they employed like lots of graphics engineer to, this interstellar scene, right, where the sea goes up basically into the scene space, right? And why I listed this work is because this work, which is kind of doing photorealism for rendering from 3D, they use lots of 3D data to come up with the photorealistic rendering. They use gaming engine and everything, but still they are confined, this work which appeared this year, they are confined to rigid scene or maybe driving scene to be at max, but they have not able to put it into the movie production or blockbuster movies. It's very tough. But only if we have good 3D data, it seems feasible to do so. Okay. So there was not only theoretical curiosity for me to improve this motion capture or non-rigid structure from motion, but also practical curiosity. There are other motivation also, which kind of I have not written in the paper, but just to make it completion, it also helps us understand the gap because it's going to hit the foundational work. So it will understand all this, how much we have progressed in this field, right? And maybe I'll find some novel constraint, that will help the data-driven approach to solve this problem. Then it's algebraic framework, it can help other fields, okay? So enough of motivation, let's get back to the formulation, okay? But before I get to the formulation, I want to define or take this opportunity to put my definition to organic prior. So this is the prior, I'm not trying to assume something. It comes as automatically mathematical derivations, okay? Previous method kind of ignore the variables as you are deriving this. But what we found is when you're deriving this, there are already a lot of information in the derivation which were ignored. So use those information to solve the problem in a much better way. And that's why I call it organic, because it comes naturally as a mathematical derivation. And what we found is that because it's a derivation, it carries over different steps of mathematics. Okay? And its existence was found to be independent of camera motion and 3D deformation. So that's why we call it organic prior. Okay. It will be more apparent as I go through the presentation, through the work. Okay. So now let's understand experimental setup. You are given a measurement matrix. I'm going to show what it is. And the goal is to factorize this measurement matrix into rotation and shape. Simple. You know that you have done lots of matrix factorization, but the only difference is you have to factorize in a special form. One has to be rotation, another has to be shape of this dimension. And as I have already quoted, this is the expected output that we want, and the assumptions are same as the seminal work that we did in this area, that has existed in this area 20 years back. Let's understand measurement matrix. Okay, you are given track points. You take for per frame, put it as 2 columns of the matrix, XY, like UV coordinate. Okay, you do it for next frame, and you keep doing for all the frames. And then you end up with this measurement matrix of dimension 2f cross p, right? For all p points over all frames. Okay, clear? I hope this is very intuitive, right? Now, one standard practice is because translation is extremely hard to solve per of scale, you basically mean centralize this matrix. So what I mean by that intuitively, remember this, I told about this trajectory, if you track these points, you basically remove the translation component, okay? It's still in the image space. And then you end up with a measurement matrix on which we're gonna operate, okay? Let's understand from simple math point. Jth point, ith frame, ith camera, okay? And this is the projection. We have to go from left to right, okay? This is the orthographic camera for ith frame and 3D point, jth point, okay? I'm going slowly through the construction, okay? Same thing, but now let's write it for all points for one frame, okay? What we're going to end up with all the points, right? This is 3 cross 1. It will become 3 cross P. Right? Same frame, ith frame for all the points. Let's understand in matrix form. This is what I've written. First frame, all the points. Second frame, all the points. Keep doing this for all the frames. Okay, you end up in this form. So this is what I have written. And what the goal is to go from this input to the right hand side with the rotation matrix. You have to solve, and then you have to solve shape matrix. Okay? I call this as master equation. Perfect, no problem. Let's see. Remember, we made an assumption that the shape is low rank. So I can basically represent shape at any frame as a linear combination of some k. K is a scalar, 5 basis shapes, let's say. Not all basis, not f, but k, some constant. This is like a hyperparameter. Okay. So we're going to substitute the xi here in the matrix, and we're going to end up in, if you do some linear algebra, you're going to end up in this kind of form. Okay. Easy to do, no. And then you realize that the rank of W is less than 3k, just like linear algebra. Simple. Okay, fair enough. So I can factorize this W to rank 3k using SVD. You can do that, right? And you can come up with 2 basis matrices, M hat and B hat. But you know that that matrix is not going to be unique because you always have this ambiguity. But remember our form. Our form says that one has to be rotation and one has to be shape. Okay. So that I can constrain this because rotation lies in a manifold. It has some properties. I can use that, right? So let's write it for one frame. I can write it for one frame because I minus 1 is to 2i is like one frame. For one frame, I can have UV coordinate, and you have GK for that frame, and then I can write this. Left hand. Same equation. I can impose orthonormality constraint, right? Because rotation has to follow this identity matrix. Okay, I can substitute and get this form. Too many variables. Let's put one UK for GK transport. Same thing, right? If you do some linear algebra, you're going to end up in this form. Okay. I'm just skipping the derivation here, but this tells you that the solution of QK lies in the null space of A. That's a constraint. And then there was a theory in 2004. They have derived it that the solution to QK should lie in this linear subspace. This is the linear subspace of this dimension. Okay. I'm skipping the theory. And this is the paper developed by Uchar in 2012. What they did is, okay, there's one more constraint here. I can put a rank 3 constraint. Okay, fair enough, because it's coming through linear algebra. But we realize that rank 3 or rank minimization is an NP hard problem, exact rank minimization. So you relax it with trace minimization. Okay, and these are the constraints which is coming from here. Okay. They solved it. They also got the best paper for this. Okay, very fair enough. But remember, when we are doing this SDP minimization, we didn't end up in an exact rank. What they did is, once you get the solution to this, you take SVD and pull out the 3 columns, independent columns. That's what they did in their solution. Okay, just to impose rank 3 constraint. All right, let's see some intuition because those equations are boring. Let's see intuitions. Okay. So you can think of this null space as a plane, and this rank 3 cone constraint as a cone, and then you have a better constraint, and then you solve this minimization. You end up in a good minimum. This is what they did. Again, I have listed. Now it looks simple to me, but when I try to investigate, it was painful. Theoretically, everything comes out to be true. Everything is nice, but then why it's not performing well? And then I realized that there are k such possible cones, not one. There are k of them. Okay. I said, okay, why they are ignoring that? And then there was no profound reason for ignoring them. I call it as organic prior in rotation because I didn't manufacture them. It's coming through the derivations. Okay. It's coming through the derivation. They're just ignoring it. They're just eliminating it. Okay, let's understand intuitive. This you know. You can understand that they solve the rotation for the first rank 3 case. They left all others. So if you solve rotations for other k, you end up lots of solution of rotation per frame. Okay, then why they ignored it? What I did is I registered on a common reference frame all this rotation. Intuitively, it looks like this. So when you register, it comes closer. Now I have 5 rotation evidence per frame. What do you do when you have more samples? You take average. That's the best estimate, right? Exactly what I did. But then this is a manifold space. This is not a Euclidean space. So you have to go some iterative algorithm. I have skipped it. That's called Weisfeld algorithm in literature, but just for simplicity of presentation, I have ignored it. Okay. But assume there is an algorithm which can solve for you average on manifold space. Okay. So I have to solve it for per frame and I come up with a better rotation. Here is the intuition for one frame. You can do it for all frames similarly. Okay. I have just listed in words the same thing, not important. As far as the intuition is concerned, that's fine. So this is the algorithm I use to solve averaging. Okay. Remember our master equation, W equal to Rx. Now I have solved rotation. I can get shape. Simple, right? Very nice. So at least this is one possible solution, if not the best solution. This is a solution. Okay. Let's compare the stats with the previous method that ignored all the other prior rotations. You see the difference is huge. It's not just 1% or 2%, it's almost like 20% or so. Because this is a relative. If you have to multiply with 100 to get percentage. This is the metric I've used to estimate the error with ground truth and estimate it. Okay. But this shape that you are recovering may be coplanar. Okay. There are algebraic reasons for that. I give you some intuitive reasoning. Why? Because camera is rigid. And if you're trying to have this inverse relation, what you are recovering is a rigid component only. So that's why you have a planar in every frame. Okay, it may happen. It's not like a necessary, but it may happen. Okay. There are theoretical reasons for algebraic reasons for that, but I'm just skipping that. Okay, so what to do? Have more constraint. Okay, that's what they did. Remember, this is a master equation constraint, and then you have a low rank constraint here. Okay. Wait, we have one more. We have already one solution here coming from previous equation. Why we are not utilizing it to better constrain this problem? We call that as organic prior in safe space, because I'm not manufacturing, it's coming as I'm deriving it, right? So do some weighted nuclear norm minimization, wait during minimization. And that is because I already know some prior on the singular values of the shape, right? So the better singular value I have, I'm gonna penalize less during minimization. That's why inverse relation, okay? And these are two small positive constants just for the boundary condition, okay? Because the singular value can be 0, it's a low rank space. Further observation is that the first singular value generally turns out to be good. Why? Because your camera is rigid. You have already, at least rigid component, you have recovered well. So why you are penalizing that again? Let's remove it. So you preserve that first singular value during minimization. And this is in compressed sensing literature, this is called like a partial sum minimization of singular values. So I proposed combination of weighted plus partial. Fair enough. Let's see some results. Okay. Here is some story. This is the method, the black one that you are seeing. It's basically proposed in year 2022-20 last CVPR. They claimed global minimization with better minima and everything. I did these simple tricks and then I have better minima than them. And we also converge faster with our optimization. They used to take 150 iteration, I can converge in 80 iteration, and I have better minima. And it's coming from Lund University people. They do this mathematical research. Uh, I have asked them why it's happening, and they are not able to explain. You know. This is some like why you should go for organic prior and thoroughly prior free, because I'm not doing any changes to the algorithm, just I'm using mathematical derivations to get better results. Okay, let's see some more results. This is prior free method, which I'm quoting. It's also referred as DMM sometimes. You see the difference is huge here. These are some stats which I compiled. This is the metric used for that. And this is the other metric we used on other data set. And we have better results than the claimed global minima papers. Here are some more results from visual viewpoint. And when I say structure for motion, camera is very important. What I mean by that is this. These are the camera trajectory time. I'm moving camera in a circular motion, flyby motion, linear motion, and everything. And you can see the performance changes. And that's why camera is very important when you are doing either structure for motion or non-rigid structure. And this kind of evaluations are required, basically. And I just evaluated it, and our algorithm is very consistent with other methods. Here are some dense reconstruct. Dense means you have per pixel correspondence. Okay, just to test the scalability. And we are doing, this is my previous algorithm in CVPR 2018, I think I proposed this method, but that's more topologically driven. This is more general approach. And here is a neural network based approach, data driven based. Why I listed this, because you can see, first of all, it does not work for small clips, which is required, generally required in motion capture system, because you perform good actions for few frames, not for all frames. So you cannot afford to have an algorithm that takes thousands of frames to give some results. You cannot afford that. So I believe with our work, they can use our constraint to maybe make it work for even smaller clips, but they cannot perform. Moreover, their performance are not there, basically. This is camera rotation error. There are not many data sets they calibrate camera, but there is some data set from CMU of I found they have some camera, and we perform consistently well, basically. So if you look onto this metric, this is just 10 to the power minus, very close, very close. Here are some more visual results on motion capture system. I have shown both shape and trajectory just to show that, okay, my trajectory is also very consistent with the ground truth, not only global metric. And yeah, just for from an intuitive viewpoint to understand this. Let's see some more challenging results and challenging deformation, like paper clip. And again, the paper, but in stretch sequence. We also have balloon, which kind of goes to a singularity afterwards. But yeah, these are all challenging deformation to solve. Here are some more stats just for completion. We have a rotation error with noise in the tracking points, basically, and we have consistently performed well on this. This is shape, this is rotation, just for completion. There are more stats here. I don't want to go over it, but yeah, you can think of what if your track is missing for some frame. It happens basically in practical settings. So what you do is basically you solve for a matrix completion. There are several matrix completion algorithms, and you can push our method. And here is interesting stat. As I said, n equal to 1 should work better. And this kind of validates our claim, because we have kind of reconstructed the rigid component correctly. So let's not penalize it. And that's what it's trying to show with r equal to 1. This is n equal to 1, 0, 1. All right. So let's see what you can go, how we can go from here to more practical setting is, of course, time-based graphic, right? We can make a perspective camera effects, and then we can solve the problems. There are some theoretical analysis that's pending is why n equal to 1 performs the best. There is no explanation for that. It's a pattern that is found, but if you're a theorist, you want to hit here, basically. If you want to study more or get deeper into this from neural network point of view, you can do some study of invariances and treatment of group theory to solve this problem in a much practical setting in a large scale. And when I'm saying that, it might hit something called geometric learning. But I want to make a point that geometric learning is not equal to graph neural network. Okay, it's much more. Okay, yeah, you have to think about gauge symmetry, and yeah, it's vast. Okay, I want to conclude here. Okay, I know I've shown a lot of things, but I will take this opportunity to just conclude here. We showed that intermediate prior exists in classical methods. Okay, people have ignored it for 20 years. It exists both in rotation and in the shape space. And it exists independent of camera motion and shape deformation type. So I'm not making a prior assumption on how the shape is deforming. It will exist no matter what. And matrix factorization still gives you outstanding results. So the progress in this field, I concluded, is poor in 20 years. And our work has tried to give fresh air to this classical method. With that, I like to conclude. I thank my sponsors and especially Professor Gool for giving us freedom to work. Yeah.